one sort of quick announcement, but sort of an important one. So I warned everyone about this, and it's manifested itself in the second homework now. So for the most part, I think that there were some issues with the autograders before, but for the most part, they were just sort of minor things. There have been, though, pretty substantial errors with the autograder for the first problem in homework 2. We're trying to fix that. My hope is to have it fixed by tonight. What I would recommend is that if you're working on the assignment, do the assignment to your own sort of liking, so it works locally, and then don't submit that part to Autolab. Start working on the next portions, and we hope to have that fixed as soon as possible. We'll send out an email when we do have it fixed, so you can wait until you see an email before we fix that. Because of this, we'll make a few changes here. I'm a little bit hesitant about some of these, but the second one in particular, but I think it's still probably for the best. The first one is that the participation questions, don't worry about that in the first homework problem. We won't count those negatively. In general, we've asked people not to do an exhaustive search before they post anything. But because things are changing a little bit, it can be kind of a little bit confusing, so we won't count any questions. Still use the search function. Don't just ask things that you see exactly before, but it's fine if you want to post things without worrying too much about what has been asked already. The second thing, and this I'm going to do, but I'm a little bit nervous about it just because I know people always expand to the deadlines that they're given, and it'll ultimately maybe give you more work, is that we are going to push back the deadline even a little bit further. What we're going to, the thing is, I don't want to have the homework due too much longer, because then with the 3 late days additionally, that gets very, very long before we can release the solutions. So what I'm going to do instead is basically say that the current deadline is Friday, so you have effectively until Monday to submit, because you have the 3 late days. We're just going to let everyone go ahead and submit to Monday without counting late days against you. So your late days on this assignment will not count. Please don't wait until Monday. But that does mean that the Monday's a hard deadline. So think of it as free late days. Don't think of it as a new deadline, even though I know that's very hard to do. But please do submit earlier and submit often. Hopefully people got that from the first assignment as well. But we won't count late days against the homework too. Hopefully that's a good trade-off, and still gives you time to start working on the next assignment once it comes out, because that one will come out next Wednesday on schedule. So, okay. So today's lecture is about graphs and networks, but we need to finish up first our discussion on matrix libraries, NumPy, and also talk a little bit about sparse matrices. Now, one quick thing is I know we're getting a little bit behind schedule, and that actually was somewhat expected. What I'm going to do is I'm going to compress. I don't want to skip over these lectures because I think the material here is very important for data science. Networks, matrices, these things are very, very core to data science. What I will compress a little bit, though, is lecture on geographic information systems. They're very important as well, but I think they are of less importance than things like matrices, graphs, text analysis. These things are typically more important for general data science problems. So I'm going to compress the GIS lecture a little bit to make up for this. And then we'll start the next section after that, should all hopefully be aligned. OK, any questions about this or about anything else that's going on right now? Not about the homework, because I know this is probably causing a lot of problems right now. But any other questions? I see. So the question was the tutorial. How much time are you going to have to do it? So it is due on a week where there's the Monday after an assignment's due. So it's not due the same week as an assignment. But the idea is you should be working on it the whole time while you work on the assignments too. So it sort of is done in addition to those things. And in fact, there's also a midterm or like a midway report that's also due, I think, on an off week, not a homework week. But the idea is you're working on it the whole time since it's out. The main deadline there is that next week there's a one sentence, and please don't go crazy with one sentence. I know you can have a lot of, maybe we'll even limit the characters or something like that. A very, very short description of what you're going to work on. We're just going to do that to basically, I don't want to give out suggested topics right now because I don't want to limit people. I don't want to sort of unnecessarily guide people into a constrained area. But then we do want to make sure everyone's sort of working on something that seems reasonable. So we'll give feedback within a couple days to everyone's assignment, just saying, yes, Basically, no actual feedback, just saying yes, no, or try looking at this instead, or maybe expand to this. It should be, hopefully, most everyone is just yes. OK, so let's go now back to linear algebra. All right. So when we stopped off last time, we were talking about the NumPy library. And NumPy library is a library for manipulating and working with arrays, multi-dimensional arrays, and matrices. It actually does both those two perspectives on matrices. It can handle operations for both of them. So in particular, NumPy has a bunch of ways to construct 1D and 2D arrays. For example, I think I actually went over this slide the last time, but you can do things like if you pass a list to the numpy.array function, that'll create a one-dimensional array. If you pass a list of lists, it'll create a 2D array. Each list you pass has to be the same size, because arrays really, in this format, have to be, each dimension has to have the same number of entries, or each row or column has to have the same number of entries in it. But you can create them like that. There's also some helper functions. So the ones, zeros, and random.randn creates a array of ones, zeros, or random normal entries, respectively. And you can create multi-dimensional versions too. So notice actually there's one little difference there. For the ones and zeros, you pass the size as a tuple. And for the randn function, you pass the size in different arguments to the function. You can also create the identity matrix. That's a 2D array with ones at the diagonal, zeros everywhere else, and you can create diagonal matrices. OK, so now let's talk about these next two slides are actually what you're going to mainly, well, next three slides are what you're going to mainly do with NumPy. So the first thing is that within NumPy, there are several different ways to index into your array. And the most common, and I'm showing actually here only two-dimensional indexing. If you have a 1D array, you would just pass the first of those two items. So the indexing is actually identical. There's no difference in indexing there. You just only pass the one or the other of the elements, not both. So the syntax for indexing into multi-dimensional arrays is you separate your indices with commas. But there are ways of, you can index just by, if you pass two integers. Indexing is always by integers here. Unlike data frames, you can't index an array by keys or anything like that. Indexing is always by zero-based integers. If you just pass an integer for both of them, you get just the single entry there. If you pass a integer for one of them, or a colon for one of them, it means to select the entire, in this case, the entire column. I think I'm running out of batteries here or something. Oh. All right. Hopefully everybody heard most of that. They did. OK. You can use slices. So in Python, the slice notation is one integer colon another integer. You can also optionally pass a colon a third integer, which would be a increment. So you can increment by not just by 1, but by 2, or by -1 if you want to count backwards. But that's sort of all fairly standard, those first three ones. The next type of indexing you can do, there's two sort of fancier things you can do to index into the items of a NumPy array. And these are integer indexing and Boolean indexing. And I should also mention, all this code is on the website. So I'm going to go over a few quick examples to illustrate certain points. But these things are just kind of general. These are sort of general techniques here. If any of these don't seem familiar, or if you're not quite sure what I mean by them, just execute the code and play around with it a little bit, and then sort of learn, hopefully, that way. Anyway, if you have an array of integers, so in this case, the array itself, there's an array called idx_int, which is an array with the integers 0, 1, 2. You can pass that array as one of the indexes into the NumPy array. So I can call A with brackets and then pass for one of these. It could be either one of them. But you can pass for one of them. You can pass this. Oops, I didn't write this properly. It should be index_int. I got a little fancy in my writings there. I think I probably had IDX already defined in the environment elsewhere when I ran it. I'll fix that on the slides and in the notebook. So this will this will return a new array with the fourth column, the index 3 column, and the rows 0, 1, 2 is what that will return. And I'll get actually to how you can combine those for both rows and columns in a second. But the other way you can index into things is with Booleans. So I can also create, so this is an array that has integer indexes, and the size of the returned slice of this array is going to be equal to the total number of entries in that index array, right? And by the way, these don't have to be in order here. So I could have written them in whatever order I wanted, and they would actually flip the order properly to, first return, say, the second row, then the first row, then the 0th row. Okay, so they could do it. You could do it in whatever order you wanted. Boolean, and by the way, that actually also means that that's relatively slow, right? Because the way that works is that you can't do anything but just sort of march this thing in order and take that index there, first index 1, add it in, next index 2, add it in, next index 3, add it in. So actually, if you're sort of agnostic and want just this thing where you kind of want them in order, just use Boolean indexing instead. So Boolean indexing is and now I create another NumPy array where instead of integers, the elements here are Boolean values, right? So they're either true or false. And the size of this index has to be the same as the size of the matrix or the array itself in that dimension. So in this case, the A, I think I created it on the last page. A in this case, I'm using this one, which is 5 by 4. So it has 5 rows. So I create a Boolean array with 5 different values here. And I index into A, passing what should be this index underscore bool here. And this will also give me a array of the first 3 rows of this 2D array, and I never know whether I call it the third or the fourth column, but I'll just call it the third column and talk about 0th columns as well. So those are both fairly standard ways you can sub-select only certain rows and columns of a matrix. But they both require you to create a new array. It can't be a list. It has to be actually an array here to index into these things. The last thing I'll say is that you cannot do fancy indexing in 2 dimensions on a NumPy array. That actually does not work. I'm not quite sure why. I think there's probably a good reason for this, but I actually don't know what it is. If you have like index bool 2 here, and index bool 2 here is a Boolean array that is that has 4 entries. So that is the number of columns in the matrix. So I can pass index bool as the column indexer here. If I try to do this does not what you want. It'll return something that is not the subset of these rows and these columns. I don't know why, but it doesn't do that. This is what you want here. So you have to do 1 first, select all the other rows, and then all the rows, and then select the columns you want. I'm not quite sure why, but this is a hang-up a lot of times. I've hit that problem a lot before I learned this, so it's a common failure mode. I'll talk a little bit about some of these in a second. I'll go through some examples here, but I don't want to spend too much time because you can go through this code, and I don't want to. We have to get to graphs pretty soon. All right, now let's talk about some basic operations on arrays. You can add arrays, subtract arrays, and actually for addition and subtraction, these are just sort of element-wise operations here. So it doesn't really matter whether you think of them as matrices or arrays. They're just element-wise operations. In order to add 2 arrays, they have to be the same size. So if A and B are different sizes there, this will throw an error. If they're the same size, it'll be OK. But this next bit is important. So if I use the multiplication symbol here, this in Python, in NumPy, is the element-wise multiplication. It is not matrix multiplication. That is a different command you have to do something different with. You can do this, but it is taking each element of A, multiplying by the corresponding element of B, and that becomes a new element in the array. So just like addition, but with multiplication instead. So just know that is not matrix multiplication. There are actually, in Python 3, which we're not using this course because there are a few libraries that don't support it, there's actually an operator for matrix multiplication, but which is nice. You can use that, but we aren't using Python 3 for this course, so you can't use it, unfortunately. Division, similarly, is just element-wise. And actually, no, the operator is fine, but I actually don't mind using the notation that we're going to use in the next slide as well. OK, so the next thing is if you want to multiply a 2D array, and I'm trying to avoid saying matrix here, but a 2D array times a 1D array. Again, this is not matrix vector multiplication. What this is actually doing is requires X to be the same number, have the same number of elements as A has columns. So A here has 4 columns, and X has 4 elements. And what this actually does is this scales the columns of A by X. So it takes each column, multiplies by X, and that becomes the new matrix that's the same size as A. Okay?
The size of X is number of rows.
Number of columns. Scales the columns by.
So it's actually multiplied by the vector X.
So the question is multiplied by the vector X? No. A matrix vector multiply will give you a vector. This returns a matrix. So it's very different. It's scaling. So if you want to know the linear algebra equivalent, this is the same as multiplying by a diagonal matrix, where by diag of X, essentially. Okay. So it is not the same as matrix multiplication, matrix vector multiplication. If you want to scale the rows of A by a vector, or by a 1D array, I should say, this is the trick to do that. So don't worry about this. Because if you multiply on the other side, that actually doesn't work either, because that does something different. So it's actually, this is the operator you want. Just remember that, or again, if you can't remember, type into Google, how do I scale the rows of a NumPy array by a vector, and it'll pop up this thing. It basically has to do with some sort of complex indexing that NumPy uses. This one is useful enough that you might want to remember it, but other than that, I wouldn't worry about those things. Just look them up on Google when you need them. A.T is a transpose operator. So if you have a 2D array, it will flip the rows and columns. Now, very important actually, this operator does not do anything. Okay? It doesn't move memory around at all. All it does is, remember, we talked about how NumPy arrays, or arrays in general, could be either row ordered or column ordered, right? So there's 2 different ways of thinking about how you order the entries in memory in an array. And all this will do is this will just flip the bit in that matrix object to say if it was column ordered, now it's row ordered, and if it was row ordered, now it's column ordered. So actually, it doesn't actually move memory around. So it's very fast, but it doesn't actually change things. So if you're inspecting the memory and call this, it will look exactly the same after you do that. And also, very importantly, x.transpose. That does nothing. It actually does nothing at all. So in NumPy, there's no notion for a 1D array of whether it's a row or a column vector. It's just a 1D array. So x.transpose actually does nothing. It's a no-op, really, nothing at all. It doesn't even swap any ordering. And so whether you want row or column vectors, kind of in the linear algebra sense, that will actually only come in when you start thinking about the matrix multiplication operators next. But just know that this will actually do nothing. It will not give you a different type of column vector. It will just do nothing. OK, so now let's get to the actual. This is all kind of still far away from matrix land here. And now we enter into matrices. So there really are 2 matrix operations that we're going to care about for this course. These are multiplication and solving. So solving linear systems, or inversion, but really it's just solving linear systems is what usually matters. So for matrix multiplication, there actually are special meanings of this function that encode what we mean by matrix multiplication depending on if we're multiplying two 1D arrays, a 1D and a 2D array, a 2D and a 1D, and a 2D and 2D. That sort of captures all the actual, because right, matrices, linear algebra does not easily at least go higher than 2 dimensions. There actually are generalizations to this for tensors, but typically you think of matrices and vectors, 2Ds and 2D arrays and 1D arrays. And the dot function here captures all those cases. So if I have two matrices, so here A is 5 by 4, and C is 4 by 3. Remember, those matrices are the size. Now matrices they are, or think of them as matrices. Those are the size where you can multiply them together, right? The way to do that is to call A dot C. Again, in Python 3, there's another operator, but stick with A dot C for now. It works pretty well. And that will return 2D array, and that array will be 5 by 3, because that's the size that you would have when you multiply those two matrices together in linear algebra. A dot Z, Z here is a 4-dimensional, sorry, not 4-dimensional, well, I guess depending on how you define dimensions here. A is a 1D array with 4 elements, and the matrix vector product A times Z. Actually, maybe I think this is sort of apparent, but maybe I'll write some of these down. Let's put this up. I have to figure out which how to. So I want the left. I want the right display. I think. That's the wrong one. I wanted the other one. It's hard when this is upside down, and I'm not sure which direction they're talking about. So if I have a matrix, A, which is m by n, and I have a vector x, which is in Rn, then the product Ax is going to be a vector in Rm, right? And so in this case, calling A dot x, the first element being a matrix, second one being a vector, will return a vector, a 1D array that has, in this case, 5 elements in it. Right? And finally, if you have a, actually I'm going to do the final one here, but the next, the third case is where both x and the thing you dot it with are both vectors. That will just return a scalar value. So remember, if x and y are both in Rn, then x transpose y is just a scalar value, and so this will just return a double value. Now it's important that this is sort of the size, the number of dimensions of these returned arrays are important. So this first one will return a 2D array. The next one will return a 1D NumPy array, and the third one will return just a scalar value. It's not an array at all. It's not an array with one value in it. It's actually just a scalar value. These are all different in NumPy. And I might try to go through this if this is confusing in a second, but we'll see if, maybe I'll just do a quick poll of the class to see if it seems confusing or not. Okay, so then the last thing is the matrix vector multiplies with a vector on the left-hand side. So in sort of our notation here, if I have what do I use there? Well, I used Z here for this one. So if I have a vector y, which is m-dimensional, the linear algebra way of writing this down, multiply with A, would be something like y transpose A, right? Because in order to multiply y by A on the left, you have to transpose it, and that would actually create a row vector, which is essentially a matrix, which is 1 by n, right? Or you could also do, if you don't like row vectors, then you can do this. You could do A transpose y, which would be a vector just in Rn. Right? One's just the transpose of the other. Now, because NumPy doesn't know about row vectors or column vectors, all these things are actually kind of the same. So, for example, I can call the normal thing of A transpose dot y. That would just be transposing A, multiplying it by vector y, and that would give us this thing here. Now, this thing here does the exact same thing. right, y dot transpose dot A does the same thing. Putting the vector on the left does the same thing. It multiplies sort of by effectively the transpose of that vector. Which, by the way, because we know that this thing is a no-op, we don't transpose 1D arrays here, it's the same thing as this. So when you have a vector on the left-hand side, that's doing actually this thing, but returning the result as a 1D array. Because again, we don't distinguish between row arrays and row vectors and column vectors. So you couldn't do this. You couldn't do a dot y because that's not the right size anymore. That throws an error. But these three things all do the exact same thing. They return the exact same quantity, a 1D array, which has in this case 5 elements. Right? So if you are used to, say, MATLAB notation or R notation, this seems weird because this is actually not really mathematical anymore. It's doing something weird where like you shouldn't be able to call this function here because it's not actually the right sizes. Once you get used to it, though, it is fairly standard. These are the only cases there actually are, and so it's very easy. You have to just be cognizant of the size of the objects that are being returned by the different functions. Who did that not make sense to? I shouldn't ask that. Actually, that's always embarrassing to pull these things, right? Who would like me to go over a quick example with these things in a notebook? Okay. People are like hesitant. Some people want, okay. Let me try to do it really quickly. Actually, after I do the last thing, I have one more slide here. So I'll just finish our last one. I'll do an example of this too. The last thing I'll mention is inverting a matrix. So if we have a system like this, so A now is going to be M, ignore all this. Next case, A is going to be N by N. And let's assume it's invertible. And X, or rather, I'll call it B to be consistent there. B is a n-dimensional vector. Then we can compute the following quantity, A inverse B, in a few ways. The first thing we can do, so I'm just forming two matrices there, a 2D 2x2 matrix and a two-dimensional vector. Again, in vector land, dimensions are the actual number of elements, so I'm going to screw that up again. But in matrix land, or in NumPy land, it's actually the number of different dimensions of the array. So a 1D array with 2 elements. I can do 2 things. I can either use the numpy.linealg.inv call for inverse, and that will actually form the inverse of A. Then I can multiply that by B. So I could call that first thing, and I could say the whole thing dot B. That would give the solution of A inverse B. But don't ever do that. Right? You should. Does everyone know why you shouldn't do that? Yeah.
I mean, I have some guess, but it's not in all cases. I mean, when we want to calculate the inverse matrix, actually it's the same as calculate solve the linear equation n times, where the dimension of matrix is n. But if you want to do it like 100 times n times, it's more worse to calculate inverse first and then apply it.
I think that gets all the right answer. I won't repeat the question. I won't repeat the answer because I think it's. But I think it gets the main points. So this has to do actually with a couple issues, and it has to do with numerical stability and with the actual raw speed of these things. So when you solve a linear system, if I actually want to solve this thing, then internally my computer does actually not compute A inverse. What it actually does is it computes what's called an LU factorization of the A matrix. So it writes A as the product of 2 matrices, L and U, where L is lower triangular and U is upper triangular. This is just sort of an aside. You don't need to know this, but it's good to know, actually. I guess you don't need to for the class, but it's good to know. Now, when you solve this, you actually don't compute these inverses either. It's actually it's very easy to invert or to solve a triangular linear system. So if I have a triangular system here, where if L here, I'm just going to think about L. If L here is lower triangular, and I want to find some vector such that this vector equals this. Sorry, this vector equals this inverse times that. then I can actually just use what's called back substitution to do this. So basically you find first the one element that has to be the way it is because there's only one term that multiplies it. You set that, you plug it into the next equation, you solve that one, you plug it into the next equation, you solve that one. This is actually the exact same complexity as matrix multiplication doing this process. It's called back substitution, and it's much more numerically stable than directly forming the inverse and then multiplying by that inverse. So what's happening internally when you call solve there is that the program is forming an LU decomposition. It is then using back substitution to solve this, and that's much more efficient than it would be if you were to just form the, or actually, because to form the inverse, actually the best way to form the inverse is to create the LU decomposition and then solve for the identity matrix, which that creates the inverse, and that's just a lot more work than it needs to be. I'll get to the question in a second. The other thing is that this actually is not exploited here, but if you want to solve a lot of linear systems, what you should actually do is explicitly form this decomposition and then solve it for each one. So you just decompose it once, which is by far the most computationally intensive part. Actually, forming that is order n cubed, and then back substitution is just order n squared. Again, you don't need to know this, but if you're curious, this actually is very kind of gets to the heart at a lot of linear algebra. If you are going to solve the same system over and over again, you actually just form this thing once and then solve multiple times with multiple different right-hand sides. Don't worry too much if that is all kind of a little bit hazy. The important point, I guess, to take home is don't ever call dot inverse. Always call dot solve if that's what you want to do. Unless you actually want the inverse for some reason, don't form the inverse. There's a question there, yeah. Okay, yeah. So the question was, what do I mean by stability? So what I mean is, if you talk about these matrices that are what are called poorly conditioned. So basically, they have the matrix is invertible, but it's almost not invertible. It has like one equation that's almost a multiple of another one. These things start hitting up against the boundaries of floating point precision. And if you try to form the inverse, you're effectively forming this first, then solving for the identity matrix, and then multiplying by that, which introduces additional instability, or additional round-off error than you would get if you just did this and then solved for this. So this one will give you more precise solutions than forming the inverse and multiplying by it. Okay, so let me just quickly do one of these things now. Open up a. I know it's not up there. I'll have to also sort of work here because I don't actually have my screen. There we go. Oh, I'm kind of far away now too, so I'm going to import NumPy. So I'm going to create a 2x2, and boy, it's really hard to see. Let me maybe see if I can move this over a little bit, or just put down this other screen. Actually, now that I'm not writing anymore. All right, so if we want to create a 5x4 matrix, say, now A is going to be a 5x4 matrix, so we can also create a 4-dimensional. This is actually very hard to have no feedback. So if we write, and so A here is a 2-dimensional matrix, right? Sorry, 2-dimensional array. Now if I multiply it by x, that will give me another 2-dimensional array where I've scaled all the columns in this matrix by x. If I want to do an actual matrix multiply, I have to do A dot x. And importantly, this is now a 1-dimensional array. So it's not a 2-dimensional array that somehow represents a column vector. It's just a 1-dimensional array. Similarly, if I have another vector here that is 4-dimensional, then x dot is kind of different because I made it. Is kind of different because unlike the previous one, this actually just returns a floating point value. right? So in all these cases, depending on the size of your inputs, it will actually return either a NumPy array or a floating point value. And these are very different things. They'll be the different objects. For instance, if I do something like this, just look at the type of this. Here, let me get the other screen down. Do you want to turn it on? Yes, turn it on. If I look at the type of this thing, that's going to be a float, whereas the type of this thing is itself an ND array. So these are subtle things that seem kind of odd, but they're really important. Similarly, if you do things like indexing into columns, so if I do something like A, get all rows in the third column, that will return not a 2D array with just one column in it, but it returns actually a 1D array. And there's weird things here. So like if I do this, so if I want rows 3 to 4, but that's actually just row 3, then it will actually return a, right, because 3:4 actually just means row 3, because the 4 is the 1 plus last entry here. That now does return a 2-dimensional array. So it's, or if I do this, right, or if I do integer indexing here and say array of the column 3, that also returns a 2D array that happens to have 1 column in it. So depending on how you do indexing and depending on how you do your multiplication, you have to be very careful about the size of your returned arrays and make sure that you're properly thinking about them either being 2-dimensional arrays that happen to have 1 column or 1 row, or are they actually 1D arrays? And these are different things because they will react differently, of course, to operators you apply to them. Right? Any questions there? Yeah. Oh, I really kind of didn't zoom in very well there. I'm sorry about that. I should probably have gone like that. That's better.
So if you consider the operation just multiplication, like this star, like for example, some 2-dimensional array times another 2-dimensional array, how useful this operation is?
So you almost, okay, so the question is how useful is the question is how useful is the multiply operator without matrix multiply?
Not dot, but like this.
The other one, right. So it can be fairly useful. I mean, if you think, so the question was how useful is the dot? So if you make, say, the second one like a mask, right? So it's 0 or 1 values, then you can actually filter out entries of the first array. So there are all sorts of reasons why you might want to do that. It's just that you probably don't think of them that much in a linear algebra sense because you don't use them as much, right? So I could do something like, b equals np dot round p dot random dot rand 554, and then a times b is going to be interesting. It's going to be the elements of a that are masked by the elements of b. So there are uses for these things. You just have to know what you're doing when you do each one.
I mean, there is another question because, like, it is probably some other libraries in Python that actually interpret 2D arrays like matrices and vectors like it's normal with thinking about it, and interpret multiplication operation with star and so on.
Yeah. So I mean, just to answer the question, so you're right that when you do the dot function, if you have a good NumPy installation, it will call some optimized BLAST library to do that, whereas it will not do that for the element-wise multiplication. Or it might, but it's a different optimized function. So yes, but you have to just sort of be aware of these things. Okay, so I want to get through today, the next section today. As I said, we're not going to get through this whole lecture here, but we are going to hopefully get, I promise we'll get through actually what you need to, as far as you need to do the problem 3 of the homework. So that means I have to get through PageRank, the PageRank algorithm. Okay, so what this lecture is going to cover is we're shifting gears now, though actually, oh wait, I forgot one part of this, actually. Man, I'm going to have to rush to get through all this. But, okay, I forgot the last bit here, which is sparse matrices. Okay, so let's talk very briefly, but this fortunately can be very brief. I think this will take like 5 minutes or so. So the last thing I want to say about matrices and vectors, and this is actually just covers the this only covers the representation part. From a linear algebra perspective, these things are the same. We're really just talking about representation now, that sort of first element of matrices. It is a fact that many matrices in the real world, and we'll come across a lot of these shortly in the class, so for example in graphs, we'll come across these a lot, they are sparse, meaning that most of their entries are 0. Right? And when this happens, it's kind of a waste to store all these zeros around, right? Because they're just 0. They don't affect computation. If I multiply by 0 or add 0, it's still just 0. And they're taking up all this memory. We're just storing a bunch of zeros in these arrays. Now, fortunately, you don't have to do that. There are a set of libraries and tools for supporting sparse matrices. And these are matrices where we only store the non-zero elements of the matrix. Right? So there's really 2 ways you should know about to do this. And you'll actually do this a little bit on your homework if you're doing the 3rd problem when it comes to graphs. But even not, you should know about this, because if you do have a sparse matrix, you should always use one of these things to store it. So the first way, remember, we talked about sparse matrices, and as I said, this is really a storage thing, right? It's really about how we represent matrices that have mostly zeros. And there are actually many ways we can do this. I believe that NumPy or SciPy, which has a sparse module, has 7 different ways of storing sparse matrices. They all have their purpose, but there really are 2 that are the most common. So the first one is called coordinate format. And it's kind of the thing you would think about doing, right? So if we have a matrix where most of the entries are 0, what we can do is we can represent only those that are not 0 in the following way. We can have a list of tuples where for each non-zero entry, we store the row index, the column index, and the value, right? So for example, if I have a matrix like this, I would store something like the row index 1, again 0 indexed, the column index 0, and the value 2. The row index 4, the column 0, and the value 4, etc. Okay? And if I make these sort of lists of row index, because, for a full matrix, we're going to have the same number of all those, right? We're going to have, in this case, 6 of each of these entries here. And so what I can do is I can just store these actually themselves in just 1D arrays. Right? So this array, the data array, is going to be 2, 4. It's going to be, I'm storing it this way here, though you don't have to in the coordinate format. You can store whatever order you want. I'm just storing the numbers 2, 4, 1, 3, 1, 2. Then I'm saying these are the rows. The rows for these entries are 1, 3, 2, 0, 3, 1. And the columns are 0, 0, 1, 2, 2, 3. Right? And that is a representation for this matrix. It encodes everything that there is about it. If we want to create the dense matrix, we can, because we just take a 0 matrix and populate it with those entries. And that is a representation for that matrix. Now, this is a good format for constructing sparse matrices. Because if we want to add a new element to it, we just append an element to these arrays here. Now, forgetting the fact that sometimes you can't append arrays that well, or that's not a great operation in NumPy, conceptually, right, if these are arrays in memory, you just append one more element, say that the size of the array is bigger, and you're done. So it's a very good format for constructing them. It is, however, not a very good format for multiplying or doing operations in matrices. For example, if I wanted to say, what is the 3rd column here equal to, or the column number 3, index number 2, there's nothing you can do but go through the entire thing and just say, which one of my elements here has the column index of that one? Pick those out, and then stack those elements in that order. You can't easily index into your array or understand, even if I even want to find out, well, what is this element here? You actually have to just search through your entire array to figure that out. You can't do it efficiently. And so because of this, and really it's this sort of lack of ordering that makes this tricky, right? Because it's not ordered. Because it's just a list of these tuples, effectively, we can't really do much. So I'm writing it ordered here, but it does not have to be. And so it's important that you can't, in general, actually have any idea how to even find an element in one of these matrices. So this leads us to another format, which actually looks very similar, but has a really important difference here, which is called compressed sparse column format. And the first 2 entries of this format look exactly the same. They are the data matrix, all the non-zero entries, and the row indices for those non-zero entries. But in this case, we are actually going to require that these be ordered in column major format. So the data matrix has to have the non-zero entries going sort of top down by column and then left to right. All right? Now, once we've done that, we can do something very, very cool here. We can actually represent column indices as a different array. And what we're going to do here is we're going to have in each element, this is going to be the size of this array here for column indices. It's a different size. The size of it is going to be just the dimension, the number of columns in the array plus 1. And what these point to is these point to where the start of that column is in this data and row matrix. All right? So that takes a second to sort of sink in. What this means is, OK, the 1, 2, 3, the third element here in this matrix has number 3. That means that the third, well, the index 2 column starts at the third entry in that data, in the index 3 entry in that data matrix. Right? So, the first element there is the 3, and I picked a bad number here. They were all 3s. So let's go to the next one. Let's go to 5. So this is index 0, 1, 2, 3 here. So by 0 indexing, this will be in index 3 of this column matrix. It has index 5. That means if I look in the data matrix and look to index 5, which is the 1 there, that will actually be, it's actually the very last one. That is the start of, that is where that column index 3 starts. So where that third/4th column actually starts in memory. All right, and similarly, the first column starts at position 0. The second column starts at position 2. Third, position 3. I'm sorry that I keep messing up these. I always don't know whether to talk about 1 indexing or 0 indexing here, sadly, but hopefully this makes sense. OK, so maybe emphasize the important point here. So the important point of this format now is that say I want to find the 4, 5 element of, or sorry, well, this one that actually exists. The 2, 1 element here. So this 1 right here. I lost my pointer somehow at some point in my clicker, but this is in now the index 1 column. So I look to see where that column starts, and then I only have to search up until the next entry here, because those are the only entries in that column. And I check then for each of those, does that have a corresponding row index that actually is the row I'm looking for? And if so, what's the value in that position? So the nice thing about this is I can index into any specific column while only looking at the number of non-zero entries in that column. And that's a huge savings over having to search over the entire data to find the value of a given entry in the matrix. It also is much better for operations like multiplication. It makes these things much faster because you can exploit things like caching better than you can if all your entries are kind of randomly spread over an entire list with no actual ordering to them. But these two formats, the compressed sparse column and the coordinate format, are actually the most common formats you'll see when we talk about sparse matrices. And any actual kind of solution methodology, or any time you actually have a library, an external library, that you need a call that operates on sparse matrices, it will almost always take compressed sparse column as the input. So this is the standard for how you represent sparse matrices across almost any set of libraries. OK, any questions there? I know I was actually made things kind of difficult with keep switching between zeros and ones indexing, but hopefully it makes sense. That the basic idea is pretty straightforward. Yeah?
Yeah, so if you already have call indices, order it. Why don't we also do the row indices, order it inside each interval?
Yeah. So the question is, why don't you do the row indices ordered also? You have to pick one or the other. You can't do them both. You could have a matrix that you store both by row and by row and by column, but then you have to store that data twice. You can't. Okay. So the row indices are ordered actually. They are ordered within a column.
In the interval, in each
Yeah.
column are equal, we want to.
Okay, yeah, so that's true. So within a column, they actually are ordered, the row indices, they are ordered here, but you still have to search through them. Now, you could do a binary search if you want to, but oftentimes you don't because there aren't that many elements in most sparse matrices, so it's faster to just do a sequential search, is what's often the case. But yes, they are ordered because you're always doing it in column major ordering. Both your column indices and your row indices within the column are going to be ordered. But you can, for example, have a lookup that just tells you immediately in order one time what element is in a certain row and column. You have to do a search in one of the two dimensions here. Now, the nice thing about this is that there are lots of libraries that will do this all for you. You don't have to worry too much about it. You can construct them in a nice way, then convert them to sparse matrix, compressed sparse column format, and not worrying about the details there. A general rule of thumb is if your data is about 80% sparse, this is sort of very, very ad hoc here, but if your data is about 80% sparse or more, it's good to use these for multiplication. If it's 95% sparse or more, it's good to use them for solving linear systems. So it turns out when you solve a linear system with a sparse matrix, you actually create a factorization that is less sparse. It is still sparse, but less sparse than the original matrix. And so you actually typically need more sparsity to make it worthwhile to use sparsity if you want to solve a linear system versus multiplication. And the reason, by the way, why it's not always better is that the block operations for dense matrices are very, very well aligned with caches and with vector operations on a CPU. So they've been highly optimized, whereas those optimizations are harder to do for sparse matrix operations. So 80% is kind of the cutoff. And you can do it all with the SciPy .sparse library. You use it a little bit for the homework, but not too much. I think actually just about these calls are really the only ones you need to do. Sparse matrices have a dot function too, so you can call dot the same way you do with a NumPy matrix. Okay, so now I'm starting to run a little bit late, sadly, but we'll get through as much as we can here. Networks and graphs. So I'm going to now switch topics. I'm going to try to move this fast to get through at least PageRank today still. Definitely nothing more, but at least PageRank today, because it's on your homework. This next lecture, or next section of the lecture, is going to be about networks and graphs. We're going to first talk about what networks and graphs are. And really the lecture, though we're talking about networks here, it's really about graphs for the most part. And I'll say what I mean by those two terms in a second. Then we'll talk about some graph algorithms, and I'll finally, not today certainly, but later on, talk about graph libraries too. These are our announcements. Let's talk about networks and graphs. So what's a network versus a graph? This is somewhat of a, people use this actually a little bit differently. Some people say they're the same thing. A lot of courses will say they're the same thing. But the pretty standard terminology is that networks are the actual sort of constructs, the relationships between objects kind of in the world, right? So networks are the things that actually exist in the world, or in the virtual world. Whereas graphs are the mathematical model for representing these things. So when I say a network, I mean like a social network. I mean the actual connection between people. Whereas a graph is a mathematical object that has vertices and edges for representing these networks. This lecture is actually mostly about graphs, though we're going to, in data science, what we do with those graphs is we apply them to analyzing networks. All right, so I assume most people here have heard, actually, has everyone here heard of a graph before in the computer science sense? Okay, good. Everyone's heard of graphs, so, okay, good. So graphs, we all know, are a set of vertexes and edges. So this is a graph connecting with 6 vertices and 7 edges. And graphs come in different types. So a few distinctions between types of graphs are directed versus undirected. So a directed graph are graphs where the edges have no directionality. So for example, the graph representing a network of, say, paper co-authorship would be undirected because there's no directionality of paper co-authorship. You either write a paper together or you don't. I don't write a paper to you. I guess that would be like different definition of papers, or directed. For example, web links, right? So a web link points from one page to another. Just because it points from page A to point B does not mean page B has a link back to point to page A. It may, but it may not. There are also weighted versus unweighted graphs. So we're mainly going to talk here about unweighted graphs, where all the edges have implicitly the same weight to them. So we don't consider some edges having a higher cost or a higher weight than others. But there are also weighted graphs. For example, if your graph represents something physical, like a distance traveled between 2 points in some map, say, then of course these edges are going to have some quantity assigned to them that would correspond to the weight on that graph, or sorry, on that edge. Now, graphs are everywhere, and networks are everywhere, right? And presumably, actually, if you're in a data science course, you don't need to be convinced of how useful networks and graphs are. But I just want to show a couple examples. These examples are all from the snap.stanford.edu site. Says both graph database and graph library, so a code there coming out of a group at Stanford. And they have a bunch of these sort of large graph data sets that have since been also visualized by some people that were at the University of Florida, this group. Now they're at Texas A&M, the group that did a lot of this work here. So these graphs show visualizations of things like the road network in Pennsylvania. So I believe actually this are the two sides of if you ignore distance here and just think of the graphs as trying to place them in terms of how dense the different things are, the middle of the state actually, I believe, has much fewer roads in it than the sides of the state. So it looks like a big bottleneck through the middle of the state with two edges in the two big parts on the side. Patent citations, so this is sort of, do patents cite each other? These things are unintelligible when you look at the graph, but they just are sort of impressive to see, because this is actually a plot of the entire internet routing topology, so how routers are laid out. In 2005, it has 1.6 million nodes, 11 million edges. The LiveJournal social network that had 4.8 million nodes and about 70 million edges. And these are all actually relatively small compared to the size of some networks, like a tweets network and stuff like this that are currently being generated every single day. So it's really impressive, actually, just how much graph data is kind of currently being generated. So I think probably everyone already kind of agrees that maybe networks and graphs are important objects. A lot of people might want to work on them for their project and things like this. So the next thing I want to talk about then is moving now from networks to graphs. So when we talk about actual graphs, how do we write code that operates on graphs, that manipulates graphs, and how do we represent graphs in this code? And though it seems like an obvious question, well, right, mathematically there's a set of vertices and a set of edges, but you probably don't want to represent this as a list of, just a bunch of vertices and then a bunch of edges, because then doing things like finding all the outgoing links from a given vertex would require you to do a search to the entire list of edges, right? So it's actually very important how you represent these things in terms of how well your actual code works. And there are 3 different ways I'm going to highlight for representing graphs. And they're all actually quite important because they all have very different use cases and very different kind of benefits and drawbacks. And these are the adjacency list, the adjacency dictionary, which is less common but actually more used in practice than the adjacency list, or less commonly talked about but actually more used in practice, and then the adjacency matrix. So let's just go through these on a simple graph here. So this is a directed graph, and I want to use a directed graph here because I want to highlight the fact that edges point from one vertex to another, and if you want to have an edge going both ways, you have 2 edges, one from node A to node B, and one from node B to node A. Okay, so an adjacency list says we're going to store the graph as a list, or really an array of nodes, where each of these nodes then points to another list or another array. And again, I'm using array and list here kind of interchangeably. They are very different things, but think of these as actually being kind of arrays or lists in the Python sense, and that they're actually arrays underneath. They're just, you access them, they're called lists. So I have a list of all my nodes here in some order, and then for each of these I have a pointer to another list that points to which edges which outgoing other nodes is this node connected to? Right, so this graph here would, for example, the outgoing edge of A goes to node B, so A would have just the element B in its list. C has a link to both A and D, so C would have A and D in its list here. Now, it's easy. The nice thing about this is it's very easy to get all the outgoing links for a given node. Right, that's sort of the operation this is meant for. You just do the lookup of that node, or find the index of that node, find the edges, and just that is the list of all the outgoing edges. So it's very easy to find the outgoing links in the graph. The bad sides are that things like deleting edges, or even checking the existence of an edge, actually requires at most a scan through this list, because you have to sort of see, okay, I'm looking at my list now of all my outgoing edges. Is there an edge node A to node B? Well, I have to find the list for node A, scan through that whole list, and see if node B is anywhere in there. Right? There's no other sort of option than that. You have to at least scan through that list, and that's even assuming we have some nice way of looking up, for like a name or an ID like node B. Do we have an easy way of getting the actual list quickly for that node? But that's pretty easy. We can do that kind of efficiently. But the other way, you have to kind of scan through the whole thing. That's just the definition of what the list is doing. And because of that, and actually a more common thing to do, and this is actually what most, or what a lot of libraries do, are what I actually will call an adjacency dictionary. So this is the exact same thing as an adjacency list. You just replace the lists in the Python sense with dictionaries everywhere. So you have a list of nodes, but it's really a dictionary now, where each of these nodes is a key in this dictionary, and the value for that key is another dictionary of the edges it's connected to. Or sorry, the other nodes it's connected to. Okay? And the advantage here, this is actually a very, very nice format. The advantage here is that, remember, dictionary lookups are O of 1 operations. They use a hash function, which is a little bit more expensive than just an index-based lookup, but they're relatively fast. And so it ends up being to find, is there an edge from node C to node A? That is, first I look up in my dictionary the node C. I get its dictionary there. I look up in that dictionary, is there an element for key A? If there is, there's an edge. And both of those are O of 1 operations, the lookup operations, so they're very nice. The other very nice thing is they're very easy to modify, right? Because we can easily add new elements to a dictionary without resorting the list or anything like that, without resorting anything. We just add another element, and we've added our new element, our new node or our new edge. We can also delete things very easily, right? If I want to delete something, I just delete that key from the dictionary. I don't have to do the whole scan through. Now, a lot of this is hiding the complexity in what dictionaries actually do. So dictionaries actually use kind of a hash function and linear probing or quadratic probing, if you know about those things, to actually do this. So that they're not perfect, right? That there is a complexity there that's going on underneath the hood. But from a user standpoint, these, and sort of even a usage standpoint in the Python land, these things are very nice ways to build representations for graphs. So, for example, the NetworkX library, which we'll talk about next class, uses internally a adjacency dictionary representation to represent its nodes and vertices, or nodes and edges. So the final one I want to talk about, though, is slightly different now. Though, ironically, actually, if you think about how these things are stored in the, say, compressed sparse column format of a sparse matrix, they end up being almost exactly the same. So it's actually very interesting, the connections there. Sparse matrices that sometimes actually are one way of representing a graph. Anyway, conceptually, though, we can also think about this graph as being represented by an adjacency matrix, right? And in the case of, say, just an unweighted graph, I'm going to consider a matrix that actually has only 0 or 1 entries. And so in this graph, or in this matrix here, the columns index over what is the source node, and then the rows index over what is the successor node. And this is a directed graph here. In the undirected graph, the adjacency matrix would be symmetric, because you would always have, if there's a link from A to B, it would always also exist from B to A. But for example here, we have our node C, which would correspond to the third column here, would have a 1 in the row corresponding to A and D because it has links to A and D. Right? And that's how you kind of encode the presence or absence of links here. Now, as you might imagine, for large graphs, we talked about graphs with many millions of edges. This matrix here is n by n, right? So if you represent it as a dense matrix for those million by million, those million node graphs, you have no chance of even on disk, you would quickly run out of all the storage you could ever want. Maybe millions you could do, but if you have billions, billions squared is getting pretty big. You would not want to do that, wasting your time sending a bunch of zeros. So what we do in practice, of course, is that most of these networks are not dense. They are very sparse. In fact, we know they're very sparse because in theory, a graph can have, for a directed graph at least, can have the number of vertices squared that many edges, right? And there's nowhere close to that many edges here. These graphs are nowhere close to being dense. And this is a common theme, is that most graphs in practice are actually quite sparse. And so we're going to use sparse matrices to actually represent these things. So we use a matrix, but in practice we use a sparse matrix. And then the irony is that if you look at the sparse matrix format, it actually looks very similar to an adjacency list format. So you can go back and sort of see there's actually something very similar. So it all is sort of a matter of interpretation about which thing you're doing, but it's actually very useful to think about from a numerical perspective, or sorry, not a numerical perspective, to think about it from a conceptual perspective, to think about this graph being encoded as a matrix. Are any questions so far? I assume people mostly know this, so I'm trying to go through it fairly fast. And I assume people are going to mostly know at least the first of the two algorithms, so I'll also go through it kind of fast. But I really want to get through PageRank on, so you can have your homework. Yeah?
So how is theoretically possible if you have the dictionary in Python with, I don't know, 1 million keys, and you can do the operation of searching in O one time?
So the question was, if you have a dictionary with 1 million keys, can you do insertion in O of one time? You can. I mean, they're hash tables, and if you have a big enough sort of hash, a good enough hash function with a low enough probability of collision, you're probably going to do it in O of one time still, amortized. 1 million is not that bad for a single dictionary. It's actually quite doable. Okay, so, oops, kind of hit that microphone very hard there. All right, so we're going to talk about, now I want to move on to graph algorithms. And, there's no way to cover, in any depth, do any justice to the wide variety of algorithms that exist for graphs here. In fact, there could be, and that there are entire courses on graph algorithms and network algorithms. I'm going to cover 3 that, in my opinion, kind of get at the heart of a lot of topics in data science. But this is a personal opinion, and there is plenty of debate to be had here. So we're going to cover 3 ideas. The first is going to be shortest paths in a graph. This is the one you've probably seen before, because it's always talked about when we talk about graph algorithms. We're going to talk about shortest path algorithms. How do you compute the shortest path between 2 nodes in the graph? And we're going to use Dijkstra's algorithm for that. Yeah? There's a question there?
By using Dijkstra, when you have in data science, isn't it possible to use that Boyle's algorithm?
I'm not going to get into that actually, like the trade-offs of different algorithms. Dijkstra's is pretty good for a lot of cases. If with the right data structure, it's pretty good. The next one I'm going to talk about is yes, question there. Oh, the question was why use Dijkstra's when you could use Floyd Marshall or whatever it's called, Floyd something. You typically don't want to do that, actually, I would say. You don't want to do all pairs shortest paths. It's very unlikely to want to do that, because that's now a dense matrix over this whole sparse graph. So you don't want to do all pairs shortest paths. There are other algorithms for single source shortest path, but yeah, Dijkstra's is pretty good. Okay, the next thing we're going to talk about is finding the important nodes in a graph. So this is sort of essentially the question of, if I have a bunch of nodes, there's some notion we have of importance of these nodes. Maybe. How do I find nodes that are important? And actually, this is the problem, in some sense, that the PageRank algorithm solves. This is the algorithm that started Google. That they used this algorithm to rank search results instead of just say, looking at which page has the most times does it repeat a certain phrase. They would actually rank pages by how important they are in the graph of the internet, or the web at least. And the third one is another very common technique in data science, and in networks in general, which is this notion of finding communities. So I'll define that in a second, but communities essentially are tightly grouped clusters of nodes that are more interconnected with each other than with things outside. And I'll define what I mean by that a little bit more formally in a second. So let me go through these things a little bit here. And what I might do is just so I can cover the two things, I might actually skip the examples and go back to the examples next time, just so I actually do get the slide on PageRank shown here. But shortest path, we all sort of know what this means, right? We're trying to find the shortest path between two nodes in a network. Now there's some important distinctions here. For example, weighted versus unweighted graphs, what edges mean in a graph. Directed versus undirected, you might use different techniques for those, though Dijkstra's works well for both of them. And actually, negative weights is a big one. So if you have negative weights in a graph and you have a directed graph with cycles in it, you can theoretically have infinitely low short costs for a path by going around again and again, which you don't want to do, right? So how do you handle negative weights? We won't work here. There are also other sort of variants here. There's single source, single target, which is what we think of, kind of find the shortest path from this node to this node. There's also single source shortest path, which is find the shortest distance from that node, from one node to all other nodes in the network. And that actually is what we're going to do. It's actually more common to do that one. And then if you want to do single target, you just stop whenever you hit that target. This is the more common way to do it. And there's also all pair shortest paths, which is nice in theory, but for most large graphs, you can't do it because it's just too big to actually fit into memory. Okay, so has everyone seen Dijkstra's algorithm before here? Who here has not seen it before? Okay, so it's actually quite simple. Dijkstra's algorithm is a method for single source shortest path. So this is computing the distance from a given node to all other nodes in the network. And the way we do this is through a dynamic programming algorithm. So what we're going to do is at each node, and don't worry if that actually sounds more confusing than it actually is. All we're really doing here is we're having at each node in the network, we're going to store an upper bound, a number that we know is more than the shortest distance from the source node to that node. So at the start, they're all going to be infinite, because we don't know if there's any path at all. But we're going to store these upper bounds, and we're going to decrease that over time until they actually lead to the true shortest path. Now, what I'm showing here actually is just a way to compute the shortest path lengths. If you want to actually compute the paths, it's very easy. You just store a link also to which node led you along that path. But I think that's talked about a little bit in the homework, but I'm going to leave it out here. So the algorithm is given a graph and given a source. You initialize your distances to all be 0. To be 0 for the source, because the source has 0 distance to itself, and everything else is infinite. And I'm also going to initialize a set, which I'm going to call Q, to be the set of all vertices. Okay. And the way you actually do this in practice to make it efficient is you use a priority queue to do this. But conceptually, we're not going to worry about that actually. Conceptually, what you do is you just repeat the following until Q is empty. The first thing you do is you remove the element from Q that has the smallest value for D. So the smallest distance. Now of course, this is actually what you use your priority queue to maintain in practice. But for now, conceptually, you can just think about picking the element in Q with smallest d as a mathematical operation here. And second, for all j such that there's an edge from node I to node j, I'm going to set the distance of node j to just be either the minimum of what it already is, or node I plus 1, right? Because I can either just, that's my distance is already good, or we know I can get to node j by starting at node I with that distance and then adding one more step to that. Right? And that's it. That's the algorithm. It's amazing the algorithms that used to be really complex and have become amazingly famous. But of course, how you do this is actually a tricky issue here. How you actually maintain a data structure where you can always pop off the smallest element of some other array and track it as you update it is actually not that easy. And you use a structure called a priority queue, which usually uses a heap internally. So there actually is some sophistication here. OK, so I'm going to skip the next. I'm going to come back to these next things. I'm going to come back to a simple example of sort of applying the algorithm, but it's also in the slides. Before we go, though, I want to at least mention the PageRank algorithm, because it's also one you're going to implement on the assignment. You're going to implement Dijkstra's too. This is only for the 688 version, but 688 version is going to implement Dijkstra's and going to implement PageRank. And what PageRank does, as I said before, when we look at a network, there is this notion of kind of importance of the nodes, right? Some nodes, we believe, in this graph, say, are more important than others. Maybe we would think that those central ones are somehow more central, so they're kind of more important, right, than other nodes. And it isn't just a matter of degree either, because maybe there's another sort of part over here where there's another network, but has much less connectivity to all the other nodes, so we think that's less important than the big, large central nodes, the central nodes in the largely connected network here. So now, unlike shortest path, there's no actual right answer to this problem, right? There's no definition of what importance means. In fact, every algorithm for determining importance is going to define what that means, and it's going to give its own answer depending on what its definition of importance is. But the PageRank algorithm is one way of doing this, and as an algorithm that is historically already, of course, very important, right? It started at Google. It kind of is very famous for being how they don't do this anymore. This isn't how it works anymore. It's certainly not only how it works anymore. But they use this notion of importance on the web instead of just how well a website matched your search query to give much better results than any other search engine, anything else that was around at the time. I remember other search engines back in the day, and they really were much, much worse than Google. So it was a big deal at the time. OK, so here is PageRank. PageRank's perspective on importance is the following. We're going to consider what's called a random walk on our graph. Right? And what that means is we start at some random node, picked completely at random. We repeatedly jump to we take our node here, we jump to a random neighboring node. Of all its edges out, we just pick one at random and jump to that one. And we repeat this process. Right? So this is like a user mindlessly clicking on links in a web browser. And we do it until we reach a page with no outgoing links, and then we start over. We reinitialize randomly and start over. Otherwise, you'd always end up at one of these sync nodes. And optionally, we can also choose to do this starting over with some probability d at each time. So instead of just waiting until we hit an end to start over, we start over only, say, with probability. We always start over with probability d, and that kind of makes the thing mix a little bit better too. So we're having some probability of kind of getting everywhere. Now, the PageRank of a node is just the probability that we are in that node, at that node, under this process at any given time. So that is the PageRank. And the way it works now numerically, and I'm going to get this slide in, so I'll go through it. And I know we're almost over time, but I'm just going to go through it. Is that the way we do this is actually through matrix operations on the adjacency matrix, or on a modified version of this matrix. You can also do it, by the way, from like a purely adjacency list perspective or dictionary perspective. It's much less efficient. So definitely always use the adjacency matrix representation for these things. Oops, I said adjacency minus matrix there, I think. But it's just the adjacency matrix. So we start with the graph G and our restart probability D and some iteration count. Take T to be 100. It doesn't really matter. We're going to initialize A to be the adjacency matrix of our graph G. And then we define a new matrix P, where the first thing we do is we replace all the rows that have, or all the columns with no entries. These are pages with no outgoing links. We replace them all with ones. And then we normalize the columns of P to sum to 1. Okay, so the columns of P sum to 1. Now, if you know what sort of about probability here, what we're doing is we're creating what's called a Markov chain on this graph. This is a probability distribution that sort of says how we move from node to node in this graph, depending on the connectivity of this adjacency matrix. Then we form a slightly modified version that takes into account this actual D term. That, you know, with probability D, we're actually just going to always jump to a uniform distribution here, no matter where we are. So that's actually represented by a ones matrix. And with probability 1 minus D, we just follow P. Then I'm going to initialize X to be, oops, this should be P hat. I had M there originally. I will fix that. Take M here and replace it with P hat. Then we take our X matrix, we initialize it to be a uniform vector, and we multiply it by P hat some number of times. And this is what's called mixing our chain. So we're simulating steps as if we're in some, have some probability of being everywhere, and we sort of simulate taking all our steps. So in a purely sort of in terms of expectation entirely, and then you're done. That's PageRank. So that's what started Google, right? That algorithm right there. Those people that know what we're really doing is we're creating a Markov chain of the graph, and we're finding the stationary distribution of this chain. And of course, the actual complexity of Google was how you do it at a very, very large scale, which was huge at the time. So this is what they were actually doing, for the whole internet. Okay, so next time we're going to pick up on the examples here. We're going to finish up networks and